begin. So we spent a fair amount of time discussing morphisms between Bott-Samuelson bimodules and ignoring the fact that they're actually bimodules. And this was useful because there are a lot of maps between them that writing as bimodules would have been very painful for. But let's return to actually the fact that they're bimodules and try to study elements morphism theoretically. Okay, so we're going to go back to elements of the actual bimodules themselves. So recall that we had BS, which is R runs through over RSR, the shift, and this has a basis as a free right R module. So I chose right arbitrarily, could have chosen left, given by C1, which is 1 tensor 1, and CS, which is this coproduct element and these are sort of the canonical, this is sort of the canonical, the best basis you could find, because this is a canonical element, this is the canonical element. And these things had a degree, because of the degrading shift, this is in degree -1 and in degree +1. Now, what I like to do is I like to think of C1, the lowest degree element, as something sort of canonical, and other things as being built up out of it. All right, so we've already seen that CS is, well, you start with C1, and then you apply this endomorphism of BS. Okay, this endomorphism of BS is 1 tensor 1, it multiplies them, and then it does the coproduct. And so the image of this is exactly CS. CS is this thing right here. Yep. Yes. So this is, function notation. It's just that the function is drawn as a diagram. And so this is what we'll do to describe arbitrary elements in a sec. But so just to remember, because this is the basis as right multiplication, that means we can interpret left multiplication in terms of right multiplication in this basis, right? Left multiplication by F. Yes. Right, so this right here is this double dot thing, this broken line, is an element of end BS. So I'm applying this endomorphism to this element, and I'm getting another element. And we've already computed exactly what happens. 1 tensor 1 gets multiplied to 1, and then 1 gets co-multiplied to CS. And then the other important thing is that we have rules that allow us to turn left multiplication into right multiplication. Right? So FCS, you should be able to write this in terms of this basis and right multiplication. And while CS was the unique element which commutes with any polynomial, but FC1, on the other hand, instead we had to take F and write it in terms of its symmetric and anti-symmetric parts. And we had this relation. So in the end, it's this. And this is just another interpretation of this morphism theoretic statement. Right? We had this relation. Okay, and if we take this relation and we apply it to C1, we get this equality. All right, so now we want to use this and bootstrap it to arbitrary Bott-Samuelsons. Okay, so let epsilon, and we already talked about this a little, let epsilon underline be a 0, 1 sequence. And C epsilon was sort of, it was either C1 or CS, depending on whether epsilon is 1 or 0, right? So CS1 to the epsilon 1, CS2 to the epsilon 2, CS3 to the epsilon D. This product is taking place in BS1, BS2, BSD. So So in other words, I have a chosen expression, and I choose a 0, 1 sequence of the same length, and I get an element in this tensor product. Now, if you want to write this element in terms of R tensor O or R tensor R, it's kind of a pain because you're multiplying a bunch of terms. So there's 2 to the number of 1's terms, but that's it. Regardless, it's fairly easy to see what this is. And these form a basis of this Bott-Samuelson. This thing. As a right R module, or in fact as a left R. So how are we going to describe it sort of in this language? Well, we have C bot, which is C1, 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 yada, yada, which is also known as 1 tensor 1 tensor 1 tensor 1, the unique element of what minimal degree. And so to get an arbitrary, to get something like C1, CS, CT, just using an example, C1, C1, CS, CT, C1 or something, you would take some diagram that looked like this. Everything, of course, is colored. And apply it to C-bot. Make sense? So really what we're doing is we're saying, okay, the endomorphism ring of this thing is pretty big. A lot of the endomorphisms kill C-bot. But here's a nice collection of endomorphisms. Okay? Endomorphisms given by straight lines and broken lines. And this is actually a commutative subring. Okay? So broken line sequences give a commutative subring of this endomorphism ring. I mean, so this endomorphism ring is certainly not commutative. And one of the reasons that you know this is commutative is that it lies inside the subring generated by multiplication by R in various slots. Okay, so clearly another endomorphism of this Bott-Samuelson is multiply by a polynomial here and multiply by a polynomial there, right, etc. And this obviously is commutative because R is commutative. And because this dot can be expressed as alpha s over 2 on the left and alpha s over 2 on the right, this ring is a subring of that one. So here are some nice commutative subrings of the endomorphism.
Sorry, I missed that. So why is the ring inside which? Why is that commutative?
Because why is this commutative? Oh, because like how do you multiply them? You stack them vertically, and if I put a polynomial here, it just slides past each other. And then the fact that this is contained in that is also.
Also, if you multiply two, it's just either this is broken or
Yeah, exactly. So certainly it's also easy to see, right? If clearly the brokenness, right? But when you put two brokens together, you get an alpha s, but it didn't matter. But those obviously commute as well.
But it's that equation that you wrote. The broken things are just in terms of either f on one side or sf on the other side. It's just a linear combination of those things.
Yes. Okay. So the exercise, the useful exercise is now to do this. Take f, multiply it by one of these c epsilons, and try to write it in terms of this basis. So this should be some linear combination of c epsilon primes times some coefficients which are acting on the right. Okay, these coefficients in R. So find a formula. Analogous to this formula here. No, that pair of formulas. Okay. So, So the thing which we haven't yet used at all is the fact that that every Bott-Samuelson bimodule, in addition to being a bimodule, it's just a bunch of commutative rings, right? So this really has a commutative ring structure. Right? Given by term-wise multiplication.
Sorry, silly question, but
Yes.
are there twists on those things?
Twists?
Here you're twisted it by one, right? R for B.
Yeah. So, right, okay, so this is important, right? So if this tensor product is length D, then this is a shift by D. So this commutative ring structure does not preserve degree. It's some weird thing where you multiply two things and then subtract D from the degree, or add D to the degree, and then it's a ring structure. Yeah, so it's a non-graded ring structure. But it has a ring structure, and so we should use that. Okay, so for instance, let me give you an example of a computation. What is C10 times, or maybe I'll write, C10 times C10 for inside BSBT, okay, for some arbitrary S and T. Okay, so what we're doing is we're taking, let me use two different colors. We're taking this of C bot and we're multiplying it term-wise by that of C bot again. Okay? Now I claim that actually, instead of multiplying them, I might as well compose these endomorphisms and then apply that to C bot. So I claim that this is actually the same thing as composing these endomorphisms and applying that to C bot. Okay? So I mean, this works because you have this nice commutative subring with certain properties. This wouldn't work for arbitrary morphisms. Okay? So this is my claim. We'll get back to this in a sec. Okay? And so what is this? This thing becomes alpha t, or alpha s, sorry. And to get this through the red strand, we have to apply our operator. So this is this times t of alpha s plus the thing where both strands are broken times dt of alpha s. All applied to C bot. Okay, but then now we know what it is, right? Now this is C01 times T alpha S plus C11 times dt alpha S. Okay, so you can do computations with multiplication now, assuming you believe my claim. Okay, so my claim was that in this commutative subring, okay,
What is the 0-1 sequence? I wanted to ask. So C1, CS, C1.
so by one, oh yes, by one here I meant it's broken. Oh, so yeah, thank you. It's annoying. I think maybe it's better to just write it all out.
Because there you seem to have identity loss. There, is that okay?
Yeah, so the problem is C1 and C0, this is really bad notation. This should be like a 1S sequence, right? Right, yeah, this should be like, CS1. But the reason you do zeros and ones is so you don't care whether it's S or T. It's really annoying. This is not the best notation. I actually regretted the notation as soon as I wrote it down, but it's okay. Does that answer your question? It's annoying, and it won't be a big deal. Do the notation however you prefer. Okay. So the claim is that for phi and psi in this subring, the one mentioned over there, generated by multiplication by R, that phi C bot times psi C bot is the composition of C bot. And this is really obvious from multiplication by R. Okay? Like the composition and the multiplication are both given by multiplying by things on the identity. Okay? So this is very straightforward for things in this subring and therefore for things in this subring. But it's certainly not true in general. Okay? For arbitrary morphisms. Okay. So, there's actually, so this is one way of looking at morphisms via these sort of 0, 1 broken line sequences. There's another way of looking at elements. All right, so one implication of this whole mess is that every element is the image of C-bot under some endomorphism. Okay, so here's kind of an aside. I think we may use this once more in the course, but it's not going to be so important. Okay, which is that every element of a Bot-Samuelson is phi of C-bot for some endomorphism. Okay? Since we've constructed a basis of this form. So we already have a different basis of the endomorphism ring, though. Okay, the Bot-Samuelson, the Lightleaf's basis. Okay, and the endomorphism ring of BSW has the Lightleaf basis. So what happens when we apply Lightleafs to C-bot? Okay, so this basis that we wrote down here is parameterized by 2 to the d things. Okay? Whereas Lightleafs is parameterized by more than 2 to the d things. For each subexpression and each other subexpression that give the same element, you have a basis element. Okay? So this is much bigger. But the point is that many of these endomorphisms kill C-bot. Okay? So let's look at how Lightleafs act on C-bot. So my claim is this, that if we take some Lightleaf associated to a subexpression, and we apply it to C-bot, then you get 0 if this thing has any downs. Okay? So remember, up was just sort of an identity map. This is up 1. And up 0 is a dot, and this sends one tensor 1 to 1. So you're all good. But then down 0 was, do something and then put a trivalent vertex here. And this trivalent vertex is the de mesure operator of whatever shows up here. And this thing right here is a Rex move. And a Rex move sends C-bot to C-bot. We've talked about that several times. So this is going to send 1 tensor 1 tensor 1 tensor 1 to 1 tensor 1 tensor 1 tensor 1, and then it's going to take the de mesure operator of 1, and you get 0. Yes, this is not firm at all. That's correct. And this is a Rex move, and so what you end up doing is taking the de mesure operator. Similarly, down 1 is by the exact same thing. This cup actually factors through this map, so you get 0. Okay? So this claim is quite straightforward. And there was already this exercise from an earlier exercise which had said that there exists a unique canonical expression for any given x. Okay? Or, I guess maybe I should say there exists at most 1, because sometimes no subexpression of this gives you x. But if x shows up as a subexpression inside this expression, then there exists exactly 1 subexpression with no downs. And then we called this thing, say, the canonical subexpression for x. Okay? And then the claim, which is again obvious by this same argument, is that if you do the canonical one, and you apply that to C-bot, you get C-bot. Okay, so this is C-bot in the original Bot-Samuelson, and this is C-bot in the Bott-Samuelson associated to whatever reduced expression for x we're ending up in. Yeah, but the point is that the ones send 1 tensor 1 to 1 tensor 1, or they send 1 tensor 1 to 1, and Rex moves also preserve C Bott. Sort of just a degree argument. The degree argument will give you C Bott up to scalar. Okay? So in particular, if we take one of these double leaves and we apply it to C Bott, what could possibly happen? Either this gives you 0, or this is the canonical one and it cancels out. Okay? So, this is either 0 or just this applied to C Bott inside VSX. Which means that we have a basis, so that means our other basis, which is now also given by 2 to the d things, is take a sub-expression an arbitrary sub-expression that gives you some element x, take C Bott of that, and apply this thing.
So can you just...
Yes.
So why 2, 3, 0? Because you will get C Bott, right?
Yeah, so here's, I'll put WE and WF, and it's 0 if F is not canonical. And if F is canonical, then it's this. Because the bottom half sends C Bott to C Bott. We have a basis of the endomorphism ring given by all things of this form, where E and F are sub-expressions for the same guy. But the only ones that matter on C Bott are the ones where this is the canonical guy. So the only data is E. E is an arbitrary expression. Yes.
So this particular, like if
The canonical one?
so that the one on top of that, the one expression on top.
This one.
No, in the middle.
This expression right here.
Yeah.
This is some reduced expression for x.
There's some reduced expression for x.
Exactly.
Now, there is one for that x, right?
Say that again?
So this bottom is W, right?
The bottom and the top are both W.
And so what I'm a little confused.
One thing I could do is I could say which C Bott it is.
So that basis, it's a basis for what?
This basis is the one that's related to Schubert calculus. Like there's interesting things you can do with this. So yes, you still look confused though, Radovan. So what do you?
I am confused.
Okay. So
when can it be? What is F there?
E and F are now arbitrary expressions, arbitrary sub-expressions for the same element. So this is what parameterized our double leaves basis. And now I'm saying, actually, we only care about the ones where F is canonical. So the only remaining data is E. So this basis, this other basis, which is very different from the first basis, this is adapted to some things. As we'll see later, it's useful to some constructions. But multiplication is really hard. Okay? If you take, these things, if you take this light leaf applied to C bot, and you try to multiply it by some other light leaf with maybe a different source applied to C bot, it's very hard. Okay, who knows?
Some triangularity or some stage
Yes, there will be some upper triangularity between this thing and that. But still, the change, so, some open questions, or really, it just hasn't been really looked at all, are sort of the change of basis between these two bases. Or perhaps just multiplication rules for this, which is related somehow, and I haven't actually unraveled it myself to Schubert calculus, but this is what Jordy tells me. Exactly.
small examples?
Yes. Yeah. And then the other thing is that one implication of this is that upside down light leaf maps are injective. I mean, at least they're injective on C-bot, but that should be enough. Yeah, they're injective on C-bot, and so because not only are they R right linear and left linear, but there's R's that you can act on in the middle, and you can see that this gives a region up there, it's easy to deduce that they're injective. Okay, so exercise. Deduce that these things are injective. It's not immediate. Okay. But so these two boards we really are going to ignore for most of the time. We're going to work mostly with this other basis, because this other basis is much easier to deal with respect to multiplication, and multiplication is going to be the important thing right now.
It has to be injected because you want something in it.
Yeah, I mean, you certainly want to end up with the basis, so none of these should be 0.
Yeah.
Exactly. So, this can't be 0, and from that you can deduce. You can also deduce some other sort of linear dependence-free statements, but they're harder to write down. Okay, so let's ignore this basis, because we won't really use it that much. Let's go back. Yep.
So why is that once again you repeat the argument that that's the basis?
Well, so we know that that every element is endomorphism applied to C-bot. Okay? We know that when we apply we have a basis for endomorphisms, and we know that when we apply these to C-bot, we get things of this form. And then by a dimension argument, right? Because of this, the dimension is at most 2 to the d. We know that the dimension is exactly 2 to the d, so they must be linearly independent. Okay. So we talked a lot about C-bot. We can talk a little bit more about C-top, which is the total broken line thing. This is the sort of, I can't say it's the highest degree element of a Bot-Samuelson, because Bot-Samuelsons are infinite dimensional and their degrees go up forever, but it's the highest degree generator. Of course, there's many things in this degree that I could have chosen as generators. However, this does have the property that left multiplication and right multiplication are the same. So that makes it, that uniquely specifies it inside its degree.
The thing just passes through.
Yeah, there's a bunch of holes here, right? Okay. And so now we define this form from BSW cross BSW to R.
No, but it's the highest degree basis.
It's the highest degree basis element in this basis.
In this basis.
All right, there's many bases, right? In fact, it's also the highest degree element in this basis. So the highest degree element in this basis is when E is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay? At which point it's just a whole bunch of dots going up. Okay? So, but you know, it's also canonical for other reasons, which is the left-right multiplication fact. So lowest degree elements really are canonical because the dimension of that space is one-dimensional. Higher degree elements aren't necessarily canonical, but in this case, this guy is. Okay, so we have this map, and what it's going to do, it's going to take two elements. It's going to multiply them, and you're going to get the coefficient of C top. Yes.
Are the generators?
Nope.
No, but the degrees will be.
The degrees will be determined,
And so
but the actual generators will not. Right. I mean, the same is true algebraically, right? I mean, if you look at generators of the ring of symmetric polynomials, you can choose completes, you can choose elementaries, you can choose powers.
I mean the degrees.
Yeah, but the degrees are determined. So certainly something of this degree is a generator, but you know, it is a basis element. Okay, so what do? We take two elements, we multiply them together, and we take the coefficient of C top. Okay. Now, if you work, you know, which is an arbitrary polynomial, and we've really chosen the right action. Okay, I mean, like the coefficient of C top in the right and the coefficient of C top in the left can be very different if you think of these as bases, as right modules or as less modules. Now on, we're like fixing the right action to be special. Why? Who cares?
So this is not like a trace.
Yeah.
Not like a trace, is that what you're saying?
I mean, it really. All right. So this is symmetric
It is symmetric.
because this is a commutative multiplication. This is a commutative ring. So yes, it absolutely is. So you should think of it as a trace. You're exactly right. But it's valued in R, and this is useful. Okay, it's not valued in the base field.
No, I just missed that. BSW is not a commutative.
It's a commutative ring. Termwise multiplication. It's just R, tensor R, tensor R, tensor R. You just multiply the polynomials in each slot. Okay? So this thing is called the global intersection form. We've really chosen right instead of left. Let's do an example. Let's do just BSBT.
When you say you choose right instead of left, where is the right chosen?
Coefficient, you know, in the C epsilon basis
As a right point.
as a right module.
There.
Okay. So we have a basis here, C bot, C01, C10, and C top. C bot, C01, C10, C top. And these are associated to this diagram, this diagram, this diagram, and this double broken line. Oh, I switched things around. Sorry.
Okay. Would it make a difference whether you chose left or right?
I mean, you'd get a different answer. The whole theory would work out the same way, but you'd get explicitly different. You know, this would not be the same function.
Not be the same.
You'll see right here. Okay? And you know, and remember, our light leaves also were constructed from left to right. We chose a side in our construction of light leaves. You know, when you talk about expressions, are you reading from right to left or from left to right? That determines whether something's up or down. Yeah, we've chosen sides several times already. It's very weird. So when we multiply C-bot by this thing by itself, you get itself. Right? You apply this to C-bot, it's clearly not going to have any. It's just going to be C-bot. So there's no C-top here. Similarly, I mean, this is the identity. So if you apply it to one of these other things, you're going to get itself. So that's this. Right? Okay. So what happens when we do C01 with itself? Okay? So we're looking at this. Okay? And what is this expressed in the right basis? Well, it's C01 times alpha t. Okay? But therefore, it has no coefficient of C top. So this pairing is 0. On the other hand, if we pair C01 and C10, we end up with a dot on each. So we get exactly C top. So that's a 1 and a 1. And now something interesting happens, right? We did this before. When C10 is paired with C10, now you're looking at this picture.
I didn't follow the previous one. C10 with C01 with C10.
Yes. So when you multiply this picture by this picture, you break this line and you break this line. So you end up with exactly this picture. You end up with precisely C top.
C top. Okay.
So now if we multiply this picture by itself, now the dot's on the left instead of the right. So we now have to express it in terms of the right basis. We have to pull it through just like we did in this previous example. And we end up with a factor of dt of alpha s. Okay? Now multiplying C top times things is the easiest. If we multiply C top times this, okay, let me just break one of these. Now this thing which is on the left is actually also on the right. All right, really, any double dot which is created slides all the way through. Okay, so you just get, I guess for this guy you just get alpha s, and for this guy you get alpha t. And then for himself you create two double dots, so you get alpha s times alpha t. And here is the result. Now, you may have noticed a certain upper triangular property, or maybe lower right triangular property, because I chose the wrong order. Okay? All right, so this is not hard to show. So this is an exercise. Upper triangularity implies that the global intersection form is, or rather, the exercise is upper triangularity. And the implication is that this form is non-degenerate. And maybe I should say, not only is it non-degenerate, it's non-degenerate to degree 0. Okay? And it's still non-degenerate after quotient by positive degree polynomials. So if you tried to take this and view it as a form valued in R itself, okay, then you'd be killing everything down here. This is just a scalar, so this lives, but you'd be killing all this stuff. But you still have this you still have some upper triangularity which says that this form is non-degenerate, or rather, is non-degenerate on this basis. It has things that die. Anything in the right action of f will actually be in the kernel of this form. So you actually should mod out these modules themselves also by the right action of R. So we'll talk about this later.
Sorry, I didn't understand that. And when you said go modulo and take values in R, that is the real R.
That's the real, this is the real numbers. Yeah.
But what was the last thing that you said? I didn't get?
So I mean, I'm just saying what I mean by non-degenerate. So certainly this basis has a dual basis. That's clear. But, this is an infinite dimensional thing. And this is a graded map, and sometimes we'll see. It can't possibly be non-degenerate. I mean, you have some very, very high thing, it has to be paired against some very low thing, but the degrees are bounded below. Right? But on the other hand, if you mod out by positive degree polynomials acting on the right is 0, then this becomes finite dimensional, and then this basis as a right R module is really a basis as an R vector space. Right? And then it's a non-degenerate. Then we're doing non-degenerate forms on finite dimensional vector spaces. This is the context we will eventually be looking at. So. Yes, this is super important, and it doesn't work for this other version of the basis. So all the computations will be done with this version of the basis. If you're going to use multiplication, it's really important. So just some quick properties about this global intersection form. So it's graded in that the degree of A paired with B is the degree of A plus the degree of B. That's obvious once you work out how the grading works on multiplication and so forth. And it's what we like to call right invariant, which is the following statement. Or rather, we're just calling it invariant, but there's a right there. Okay? So the condition of being invariant depends on a side. So suppose that you take an element A and right multiply by a polynomial f, and then pair it with b. Okay? What are we doing? We're taking a times b, and then taking the coefficient of, and then right multiplying by f, and taking the coefficient of c top by right multiplication. Obviously, this f comes out. Right? And it didn't matter whether we multiplied a on the right or b on the right. Okay, so diagrammatically, A is maybe some diagram applied to C both, B is some other diagram. And it doesn't matter if we multiply by F on the right, it slides past these diagrams. So, on the other hand, so if we multiply by F on the left, again, it slides past, so it doesn't matter whether we put it here or we put it there. But that's certainly not linear with respect to the form, because then we have to slide it through the product and get to the end. So this is not equal to anything else, right? I mean, okay. So invariance, it satisfies this and this on both sides, but it only is linear on the right. So there's an exercise, and that talks about generalities of these kind of forms. So a right invariant graded form is the same thing as a degree 0 map from a bimodule to its dual. Okay, so the fact that the Bot-Samuelson bimodule is self-dual says that it has some isomorphism from itself to its dual, and an isomorphism is the same thing as a non-degenerate invariant form. So there's an exercise about this, or actually duality is finally defined, so that exercise may be fun. So our goal is to investigate the properties of this global intersection form. Okay. But actually, the global intersection form sort of, like any graded form, that pairs one degree against the other, there's not so much you can say, right? You change basis on one, you change basis on the other, you find orthonormal bases, and there's no signatures that you can talk about. Only when a form is on the same vector space, when it pairs the same vector space against itself, can you get something interesting. So degree 0, maybe this is interesting. Okay? But in other degrees, it's not interesting. So what we want to somehow do is compare the -5 degree with the +5 degree, find some isomorphism between them, and then use that to put a form on the -5 space itself, and then look at the signature of that. Okay? And this is the kind of thing which is done in Hodge theory. That's what we're going to talk about now.
Sorry, can you just repeat?
It will be repeated. So this is a new chapter. We're done talking about Bot-Samuelsons for the moment, and we're just going to do some linear algebra, fun linear algebra. All right, and I'm going to note that a lot of the stuff we're about to do is going to talk about signatures of forms, which means that it's really essential, up until now, the fact that we're working over the ground field, the real numbers, has not been important. But now, it's essential that we work over the real numbers. Okay. So, let H be a graded vector space. It's equipped with a non-degenerate bilinear form which is graded, so that it pairs H minus I cross HI to R. Okay, and maybe I'll call this particular form. Maybe I'll put a a minus I there to indicate that I'm really thinking of this as something dealing with degree minus I. Now, the non-degeneracy implies that this thing is balanced, that the dimension of hi is the dimension of h minus I. So we're only talking about vector spaces symmetric around 0. And so an example of, the key example, I guess, will be, say, take a Bott-Samuelson, mod out by the action of positive degree polynomials on the right, and equip it with the global intersection form over R, just like we discussed. So here's a definition. Suppose that you have a map of degree 2. So in other words, this is a map from hi to hi plus 2 for all I. Okay? So we're going to call such a thing a Lefschetz operator. If it satisfies, if it sort of commutes with the pairing, in the sense that if V is in degree minus I, and LW is in degree plus I, so W is in degree plus I minus 2, then this is the same as applying L to V on the left and W on the right. And so this would be in degree minus I plus 2. Okay? So, for instance, we've seen that left multiplication by any element satisfies this property. Or in fact, not even just the left multiplication. In a Bott-Samuelson, we can multiply by a polynomial anywhere. And that's part of this commutative subring, so it will actually commute. So actually, multiplication by a polynomial anywhere gives you a Lefschetz operator. Multiplication by a polynomial on the right, of course, is the 0 operator. But multiplication by a polynomial anywhere other than the right side will give you an example. So left mult by f and r, but of degree 2, right? So by f and r linear, right? Meaning a linear term can be degree 2. We only care about degree 2 operators. Or middle mult. All right, by middle I mean some spot in the middle. That also works. Right mult technically works. It's just boring. Okay. So the value of having one of these things is that it gives you a way of identifying, well, not necessarily identifying, but at least taking the degree minus 5 space to the degree plus 5 space. Okay, so L induces a form, so I'm going to call it the Lefschetz form. On each h minus I. Okay, so I'm going to use soft brackets for this. And I'm going to index it with both the degree and L, because it really depends on the operator. Okay, this form was fixed and independent of the operator. This form depends on the operator. Okay, so if two things are in degree minus I, then what I do is I take one of them to the degree plus I, and I do this by applying L I times. Okay. So anyone who's familiar with, I mean, in geometry there's a whole story. I'll discuss the connection to geometry at the end. Okay, but this really does depend on L. Okay. But again, L could be the 0 operator. So this form could be the 0 form. Okay. So we say that L has hard Lefschetz. All right, it satisfies this theorem, which is described as the hard Lefschetz theorem because it's hard. So we say it has the hard Lefschetz property, HL, if for all I, big and equal to 0, L to the I is a map from h minus I to h plus I. And this is injective. Okay? But since these spaces have the same dimension, that's the same thing as saying it's an isomorphism. Okay? And
The spaces are finite dimension.
yes. Oh, yeah. Oh, yeah. Yep. So it's an isomorphism. And I guess the third thing is that because this form is non-degenerate, this form is non-degenerate pairing here to here, therefore the Lefschetz form is non-degenerate. These three things are if and only if. Fairly clearly. Now, I'd like to point out that this definition requires this to hold for each I. One of them is trivial. When I is 0 in the middle degree, we're asking that the identity map is injective. And that this form, which is, since we're doing nothing, the same as the original form, is non-degenerate. Okay, so at I equals 0, there's no condition here. And this middle degree ends up being interesting for all sorts of reasons. The middle degree, while the easiest degree for hard Lefschetz, is the hardest degree for everything else. Because one proves these things by induction. Okay, so let's do an example. BSBT again. And L, F, is going to be left mult by F. And the important features of our linear polynomial are going to be that ds of F will be some number, I don't know, let's call it lambda, and dt of F will be delta. Okay. So how does this act on our basis? Okay. We have this guy. Here's the lowest degree.
So you want it to be non-zero or?
Say that again?
So f minus s of f by alpha a, you want it to be some lambda.
Yes. So lambda could be 0.
Lambda.
This is sort of like the arbitrary case. Okay, I mean f could be even more, this doesn't determine f, but this is going to be the only feature of f which is relevant. Right, so for, up to any two things with this property are equal up to things symmetric in both s and t. And if you have a left multiplication by something symmetric in s and t is the same as right multiplication and therefore is 0. Okay, so how does this act? Okay, so when we apply LF, then we're going to start sliding this across. Okay? So one of the terms is going to be breaking the first guy. And the coefficient at which it breaks this thing is ds of f, right, which is lambda. And what's left over after you've broken this is now we have SF here. We want to slide that through, and that's going to break this. And the coefficient it's going to break that with is dt of SF. Okay? But we know what SF is. So this is dt of f minus lambda alpha s. Okay? And so, in fact, this is dt of f, so delta, and then minus lambda times dt of alpha s, which is a ts. Okay? And then we've slid it all the way through. We have ts of f, but this is a positive degree thing acting on the right, so it's 0. So I should put this here. Okay? So by these two arrows, I mean that when you apply the Lefschetz operator to this, you get the linear combination of the things on the arrows with the coefficients given on the arrows. Okay? So now what happens when we apply LF to this? Okay? So, F slides right through this hole, and then it only has to be broken by this. So the coefficient of breaking that thing is just dt of F. which is delta. And similarly, here you only have to break the first thing, and the coefficient is ds of f, which is lambda. And what you get after you slide it through is positive degree on the right, so it's 0. And then, if we apply L to this, we of course get 0, because left multiplication and right multiplication are the same. Okay? So here's this calculation. Now, what degrees are these things in? This is degree, this is balanced, so unsurprisingly, this is the degrees -2, 0, and 2. And so weak Lefschetz is what? Right? Weak Lefschetz is the statement, well, some statement in degree 0 which is vacuous, and then the statement that L squared applied to him is non-zero. Okay? So LF squared applied to C bot. Now we see what this is. This is C top times lambda delta plus the times delta minus lambda A TS. Okay? Which is C top times lambda 2 delta minus lambda A TS. There. Times the product of two scalars. Okay? So this is non-zero precisely when either lambda is non-zero or 2 delta is not equal to lambda times alpha TS. Okay? So you see that there's a whole space of operators. Here's lambda equals 0. Here's 2 delta equals lambda ATS. And it's on either of these lines, the corresponding operator does not have hard Lefschetz. Okay, so the corresponding Lefschetz form is degenerate. And then it's left in these open regions, right? So being Lefschetz is, satisfying hard Lefschetz is a open condition. So there's plenty of exercises like this that one can do. And the first exercise, which I like, so I should give you an example without HL. So you see what that looks like. Here's an example without HL. I mean, you see it here, but here's a more sort of just abstract example. You have a 4-dimensional graded vector space where the Lefschetz operator looks like this. Okay? So, and the pairing, I just pointed from a basis to its dual basis. This is the pairing. Not the Lefschetz pairing, but the original pairing. So this has to be a Lefschetz operator, which says that this behaves in some sense with respect to the pairing. And so I couldn't just draw these arrows arbitrarily because the Lefschetz condition was important. Okay? But clearly L squared is not 0. Okay?
L squared is 0.
L squared is 0. Yes, thank you. L squared is not injective, is what I meant to say. So in fact, I did this for a reason. So the exercise is to show that BS with left multiplication by an element of F never has hard Lefschetz. Okay? And one of the reasons you should think about this, why this is true, is because BS is actually two copies of BS itself. One shifted down and one shifted up. And each BS looks like this. 2-dimensional, where L does this. So two copies of that shifted up and down look like this. And this isomorphism of BS with two copies of BS obviously commutes with the left multiplication since it's a bimodule map. Okay? So each left multiplication must preserve each summand. And so it can't get from one summand to the other summand. Okay? So this is obviously BS shifted by 1 isn't something we can even talk about because it's not balanced around 0. But some self-dual thing like BS shifted by 1 plus BS shifted by -1 is something we can talk about. And it does not have it because of these shifts. And because each summand is preserved under the Lefschetz form. Okay? So this is an exercise, although you know, maybe from the start you should do the exercise like this and compute the numbers and see why it doesn't work. Okay. Cool. But one thing that might have hard Lefschetz is left multiplication by f plus middle multiplication by g. Why? Because middle multiplication isn't a bimodule map, and it doesn't commute with the decomposition. So middle multiplication can easily break across the decomposition of BS and BS. It doesn't commute with the idempotence. Okay? So when does this have it?
On BSBS?
Yes.
But you just said that left multiplication by f is actually 0.
No, it's not the zero map. It looks like this.
Not L squared,
That all squared, yes.
Yeah, L
All squared is the
zero.
zero map.
Yeah.
But it will matter, this term here will certainly matter when you're doing this computation. Any mg itself also cannot possibly have hard Lefschetz. Because you can never break the leftmost strand, and so you're never going to get C top. But some linear combination will. Okay, so let's get back to the general properties of this stuff. So the first note is that if you pair two things in degree minus I under the Lefschetz form, that's the same as pairing L of V with L of W. Okay? Because how do you actually unravel this? Well, really, this is V paired in the hard bracket form with L to the I of W, whereas this is LV paired with L to the I minus 1 of W, but L is a Lefschetz operator, so you can move it across.
That's minus I plus 2.
Yes. Thank you. So this is quite easy. And this, okay, let's really look at what, well, so I'm about to describe things that have hard Lefschetz are like SL2 representations. Okay? Real SL2 representations. This looks like an SL2 representation if you had the grading shifted, but the grading's wrong, okay? But things with hard Lefschetz really look like and really are SL2 representations. Now I'm going to make some definitions, and I'm going to draw SL2 stuff on the side. Okay? So suppose L has hard Lefschetz, and we should think SL2 representation. And in fact, there's an exercise which says actually it is an SL2 representation. There's a unique SL2 representation. So here's my example. Here's some 16-dimensional space, and the Lefschetz operator is pointing straight up because I've chosen my basis well. Okay, so anything that doesn't have an arrow coming out of it, if you apply L, you get 0. Okay? So, you know, if you pair this guy against himself on the Lefschetz form, that's the same as pairing this guy against himself. Or this guy against himself. Okay? So there's this nice decomposition here into SL2 isotypic components. And we want to describe that. Okay? So let the primitive space in degree minus I be the elements in degree minus I such that, well, you know, if we apply LIV, we get something non-zero by hard Lefschetz. But if we apply it one more time, we might get something 0. Okay? So looking in degree minus 2 here, okay, if we start with this guy and we apply L squared, and then one more time we get 0. But if we start with this guy and we apply L squared, and then one more time we don't get 0. Okay, so the primitive space in degree minus 4 is this. Primitive space in degree minus 2 is this. Primitive space in degree 0 is this. The span of those guys. These are called primitives, and you should think of them as the lowest weights. Okay, of an SL2 representation. And this, we should, by convention, let's set the primitive in some positive degree to be 0. Okay, primitives are lowest weights. Lowest weights must be less than or equal to 0. And so this decomposition into SL2 isotypic components looks like this. In each degree, okay, what you do is you say, okay, you've got the primitives of degree k minus 2I to which we've applied Li times. This is a decomposition like this. Okay? And this is the Lefschetz decomposition. So really what we do is we think of this whole space as everything you get by applying L to these primitives. And in each degree, that's what this says. Okay, so this is the Lefschetz decomposition. And you think of this as being the isotypic decomposition. And the claim, which I'll leave as an exercise but demonstrate, is that the Lefschetz form, minus I, is orthogonal with respect to this decomposition. Okay? So suppose we want to pair this guy against this guy. They're in two different spots. Okay? Well, pairing this guy against this guy in the Lefschetz form is pairing this guy against L squared this guy in the normal form. But L is a Lefschetz operator, and this guy is in the image of L. So that means you can move the L over there, and it's the same as pairing him against, 0. Okay? So this argument always works. Okay? So, I mean, this is a general fact. SL2 representations have nice inner products, and isotypic components are orthonormal. Right? They have inner products where E and F are biadjoint, and isotypic components are orthonormal. So really, we're kind of secretly doing SL2 theory, but with only a raising operator, without a lowering operator. The lowering operator exists, but they're hard to sort of just construct. That's why it's an exercise. Okay. So here's the weird definition, but the great one. Suppose that L has HL. And H is even or odd. In other words, all the degrees are even or all the degrees are odd. So obviously the even part and the odd part never deal with each other. L is okay, so let's just stick to one of them. Okay? We say L has the Hodge-Riemann bilinear relations. Okay. Yes. Yeah.
So H0 is 0.
So H0 in degree 0, there's this thing, and then these three things, and then these two things. That's what this decomposition is. So in L0, you have the things that are of the form L squared of a primitive down here. You have the things of the form that are L of a primitive in this degree, and you have the things that are from L0 of a primitive in that degree.
So this is sort of weight spaces intersected with.
Weight spaces intersected with isotypic components. Yeah. I actually prefer to just. You're right that it's better to just think of all the ways to apply L to an isotypic component, and to think of the whole isotypic component rather than in each degree. But that's usually how it's done in the literature, so it's worth seeing. Okay, so we say L has the Hodge-Riemann bilinear relations with standard sign which I'm going to abbreviate HR. Okay. If the Lefschetz form is alternating definite on primitives. I'm going to say what that means. Okay. So, I mean, you look at the lowest degree, and it's positive definite. This guy paired with himself, which means that this guy paired with L fifth of himself in the normal pair is positive. Then this primitive space is orthogonal to this one. So first of all, if this guy is positive, then him paired with himself is also positive. And this guy paired with himself is positive. And all these guys paired with themselves is positive by this claim. Oh, sorry, not by this claim, by this note. Okay? Now, these guys, the form restricted to this space should be negative definite, which means that it's negative definite on this whole isotypic component. And then the form restricted to this space should be positive definite. Okay? So this is what it means to have the Hodge-Riemann bilinear relations. And there's an equivalent statement. Okay, so we've seen that now in degree 0, we've got a three-dimensional positive definite space and a three-dimensional negative definite space. So that's signature 0. Whereas over here, we've got a one-dimensional positive space and a three-dimensional negative space. It is signature -2. So if you have the Hodge-Riemann bilinear relations, your signature is determined by your graded rank, by how big you are. Right? I mean, because you count the dimension of the lowest space, that's all positive, and then you have positive, and the next lowest space, everything else is negative, and you can find some formula to find the signature of an arbitrary degree. Yes, this is if and only if. So signature is determined by a certain formula. Oh yeah, by the graded rank. So yeah, we should stop. I forgot about that. So we'll take a break.
Would you want to always start with positive on some end, or
yeah, so I always start with the lowest degree being positive. That's what I mean by the standard sign. And the definition of this thing when it's not even or odd is a little bit more annoying. Okay, so I'm just always assuming it's even or odd. So, hopefully, is there coffee outside? Did I? Yes. I'm sorry.
No, that's fine. No.
I got carried away.